Good morning, everyone. My name is Kelly Paffel. I'm with Swedgelock, and I oversee the steam system engineering and analysis, auditing, and also with the compressed gas work that we do for leakage correction. And today I want to talk about steam and condensate leakage and what I call a management program. The thing about what we call a management program, you go out and you find a leak and make a correction. That's only one part of the step. The next part is analyzing what caused the failure, which is basically root cause analysis, and determining what changes need to occur in the system to prevent leakage. What I tell plants, and doesn't matter what size, very small, very large, I'll allow you maybe 2 steam leaks a year, period. There's no reason to have more than 2 steam leaks. And as I go through this presentation, I'll kind of describe things that we can do today to stop leakage. There's no reason to have steam leaks. So to improve the steam condensate system, change must occur. No change, no improvements will occur. And basically, if you look at change or raise to a more desirable or more excellent quality or condition or make better. What we did in the steam and condensate system 5 years ago is not what we do today. What we did in the steam and condensate system 2 years ago is not what we do today. We continue to change to make improvements, reliability, increase production, reduce energy costs, reduce emissions. And I give people an example. I have an iPhone 5 and I'm going to upgrade to iPhone 6. So in my daily life, I change to improve what I can do as a support engineer to the world. And the same thing in plant operation. We need to change. So if there's no changes going to be done, then there's no improvements that will occur. Steam and condensate leakage has a negative effect on the steam and system in the plant operation. Steam leaks, you lose both the sensible and latent energy. The thing about steam leaks, they grow in size. The steam will erode the opening and will grow, or what we call wire draw. The thing about that is that we have to be very proactive, because if we let the leaks go, it will start to increase in size and more leakage will occur. So the increase in leakage size, the other thing, it permanently damages the components. I go in and working on flanges, and they have steam leaking on the flanges. It erodes the flanges to the point that I got to really take the flanges out and put new flanges in. So steam leakage permanently damages the components that we're working in. Increase emissions. So if I go by and I see a steam leak to the atmosphere and look at it, yeah, it's energy, yeah, safety, but it's also emissions. Because if that steam is leaking to atmosphere, it does nothing for me in the process. If it's leaking out there, then I have to put more fuel into the boiler to overcome the leaks. More fuel in the boiler increases the emissions from the boiler. So we can do calculations based on the EPA that gives us how many pounds of CO2 a steam leak will cost us, how many pounds of SO2 a steam leak will cost us. So the thing, not only is it energy, safety, reliability, but also think about emissions. I've done steam leak corrections for plants that are in containment areas. Containment means that they have to reduce emissions because they're surrounded by a city, residential areas, and they want to reduce the emissions. And the total base of the steam leak correction was reducing emissions. Steam leaks, one of the top 5 greatest paybacks. People always ask me, I want to optimize my steam system. One of your top 5, steam leaks. So one thing is that you fix it, it's instantaneous savings. The correction or improvement in the steam system has a greater payback. Everyone talks about correcting steam traps, and yes, you should correct your steam traps, but a high-pressure steam trap of 400 psi is probably failing into a flash recovery system, and you really don't lose any energy. You lose the mechanical work of it. A steam leak, you lose both the sensible and the latent energy. So it's one of the top 5. So it's a very important part of our optimization. The other thing is most leaks can be corrected without capital expenditure. That means that I'm not going in and putting in, like improvements on the boiler. I got to put a new economizer in or put an economizer in, which is a capital expenditure. Steam leaks typically don't require capital expenditure. So it makes it a very viable part of our optimization of our steam and condensate system. Steam and condensate has a negative reliability. Failures with valves, failures with connections, failures with flanges. All this will cause production issues. The thing is that, I'll give you one example, especially leakage on steam tracing systems. In steam tracing, we require 100 psi at 338 degrees. If there's leakage, we're not going to get 100 psi. We're going to get some pressure less. Any pressure less will have a lower temperature, so therefore causes production. The other thing is that we have failures out of flanges. We've got to shut down parts or segments of the plant to correct the leakage. The thing with that is, again, now I got to schedule a shutdown of that plant to correct this leak area. Safety. One of the things is a safety. Leakage is a hazard. The steam is hot, can burn. Visibility. I've got in plants that you can't walk through the tunnel area because there's so many steam leaks you cannot see. I've been in different plants where they have sections of the plant, taped off that you can't enter because of too many steam leaks. Bogs up your safety glasses and you can't see. Steam has a high temperature. Coming out the atmosphere is 212 degrees, and it can cause burn. Condensate leaks. Walking in a facility and they have condensate leaks, and the condensate's pouring down onto the ground level or the first floor or whatever floor level, and the condensate coming out is 212 degrees. OSHA says anything over 140 degrees or higher, we have to protect plant personnel from burn hazards, which is really good. So the thing about it is that one of the things we have to do is correct steam leakage to protect plant personnel from the elevated temperatures. OSHA says 140 degrees or higher. We need to protect the plant personnel. We want to correct the steam leaks. We do not want to rope off the area so people can't walk in there. We want to fix the correct leaks. Just remember the standard is 140 degrees set by OSHA that we have to protect plant personnel. What are the major causes? The thing is that I write papers about steam leakage and do analysis and everything else. Connections, threaded and tube fitting. And I'll be talking about each one of these areas. Valves, internal leakage and external leakage. Corrosion. Water hammer, flanges, piping. That's where we get most of the steam leaks are from these areas. Example. Connections. Shredded pipe. Every time I do a steam leakage assessment, number one, threaded connections. Bar none, threaded connections. People always ask me, how do I get around having steam leaks? Don't thread pipe, period. Don't thread pipe. If you get into the thread associations and the technology and everything else, we're relying on the thread itself to do the sealant. And yes, I've been through the Teflon tape and the blue sealant and the blue sealant. It's not a sealant, it's a lubricant. The thread ends up to be the sealing point. The other thing is that when you have a steam system, people have a tendency to forget it's going to expand and you're going to have contraction, expansion and contractions. So you're asking the threads to do the sealing, and you're asking the threads to take up the expansion and contraction. The next thing in the steam and the condensate system, you have CO2 corrosion and oxygen corrosion. CO2 corrosion attacks the weakest part of the pipe, that is the thread. Oxygen corrosion can attack the pipe, and it can also attack the threaded connection. The thing is that it comes down to installations. Why do we use threaded connections? We don't have to have a welder to do the welding. So it makes it a little bit easier, but it comes back to get us because we have so many steam leaks, which is causing a majority of issues. I gave up threaded pipe 24 years ago. I do not thread pipe. The thing is that I cannot afford to have steam leaks on the project I'm doing. I can't afford to put the pipe fitters back in there, correct steam leaks or condensate leakage. So I just don't thread pipe. So if you go in and have steam leaks, it's typically around the threaded connections. Welding, 15 PSI or higher. You have to have a certified welder to B31.1, which is the National Power Piping Code. In all my years of construction, and I'm continuously doing installations in the field, welds do not leak. If the welder is certified, I've never had a weld leak yet. Yet. I'm not done yet with my career, but I have not had a weld leak. The other thing is that we use, besides welding, we use tube fittings. Use of tube and tube fittings, we've been doing that for 35, 40 years. The thing about tube fittings today, tube fittings are guaranteed not to leak. But the thing is that going on plants, and there are tube fittings that are leaking, and that's because they're improperly installed. The people have not been trained correctly how to install the tube fitting. But if you install the tube fitting correctly, no problem. I'm doing a project right now where the pressure is at 400 PSI. And the plant says, well, can you use tubing and tube fitting at that pressure? Well, yeah, we use tube and tube fitting at 3,200 PSI. 400 PSI is not that very high of a pressure. So when you're looking at installations, as you can see in this picture, is a typical installation that we use, which is using tubing and tube fittings for installing a simple device as a steam trap station. And that's been in operation for 4 years now, no leaks. So, but anyway, just another way to get around using threaded connections. Flanges. People say, flanges leak. No, people make flanges leak. Today, you need the proper material selection for the gasket. I should have put it in there, gasket material selection. You need to know the proper torque specification. Today, gaskets are torqued. Don't go up there with a close-in wrench, put it on the bolt, hit it with a maul 3 times and think that is torque. That's not torque. The other thing is you have to know the torque pattern, which comes from the gasket supplier. The next thing, you have to only have axial movement on the pipe. If we think we're going to have anything but axial movement, is that we will guide the pipe. Not support the pipe, guide the pipe. A guide can support the pipe, but support cannot guide the pipe. So people need to understand the difference between a guide and a support. If you do that, then you, as you see this picture, this piping system, which are flange valves, have been in there 25 years, okay? Never really been touched because they used the proper gasket material, they used the proper torque specifications and the torque pattern. And they made sure this system here will only have axial movement on the flanges, thus have no leakage. Just remember, flanges do not leak today. So then we get talking about valves, internal leakage. And valves, we out there in the system, we use them as blow-off valves on steam lines, condensate headers, isolation, drain valves, you know, a multitude of different applications. And we get internal leakage. As you can see this in the picture, this valve is in the closed position, and it's been leaking, and the wire draw just totally destroyed the internals. The other thing that we have a problem with is on valves is external leakages, which is the packing, which comes up probably after threaded connections as a second major contributor to steam leakage. And then we have bonnet leaks. Not too often, but we do have them. The thing about internal leakage is you have to understand FCI and API standards. Any valve you put into the steam system today, FCI standard must be class 4 or higher. Class 4 or higher. The highest classification is 6. If you want to buy class 6 valves, great. That's no leakage. Or, no, I shouldn't say no leakage, very, very, very low leak rates. The API standard is 3 bubbles or less, which means putting 80 psi on one side of the cavity in the vertical position and filling the other cavity with water and counting the bubbles per minute. And API says no more than 3 bubbles per minute. A lot of vendors will say my valve is bubble tight, which are saying no bubbles in a minute. But you need to understand these classifications. If you're going out to, and not so much on the control valves, as you can see in this picture, the green is the control valve, but it's the isolation valves before and after it. If you don't specify the class shutoff, you get class 1, which is what we call a commodity valve. It leaks like a river. And you get what the picture showed on the previous slide, a tremendous amount of leakage. So the thing is, today, when you write the purchase order, as I do, is on my purchase order for my isolation valves, no matter if it's a ½ inch or it's 24 inches, I put on there either the API requirements or the FCI standard. The next thing on valves is external leakage. And one of the things people use is gate valves, gold valves. And the last great revolution we had in a gate valve was 1941. There's nothing new with gate valves. The technology didn't, accelerate or improve the valve. The technology went the other way to reduce the cost because people buy gate and gold valves by cost. And the thing is that then you get not only a lot of internal leakage, you get external leakage through the packing. And then it causes, again, major issues. Other valve types, specifically in ball or butterfly, technology has accelerated in the last 15 years. For one reason, we use them for all types of gases. And we're using them in gases that we cannot have external leakage. So why not use the same technology in steam or condensate so we do not get external leakage? But anyway, look at changes in valves. Corrosion. The thing is that in condensate system, most of the corrosion is due to CO2 corrosion, carbonic acid. In the boiler plant, we are treating it with amines. Either it can be a filming or neutralizing amine to counter the carbonic acid. The thing with the leakage condensate lines is the condensate, you allow the condensate to cool down to roughly around 204 degrees, and the condensate, the CO2 corrosion gets very aggressive and can schedule 80 piping very fast. The standard for condensate return lines should be stainless steel, but people don't do that. They're worried about the cost. But just remember one thing about condensate, 16% of your energy sits in the condensate. Why let it go to the ground? So the thing is that to keep, counter CO2 corrosion, keep the condensate temperature as high as possible. If you can get the condensate temperatures to 250 degrees, or what we call pressurized return system, then you reduce the amount of CO2 corrosion that's going to occur. If you're going to put condensate lines in, do not use Schedule 40 piping, use Schedule 80 piping, which it will last a little bit longer. Steam piping, CO2 corrosion is not very prevalent. Very, very, very seldom do I find CO2 corrosion in the steam piping. The thing is that the steam piping will have high temperatures where CO2 corrosion is not prevalent. But in steam lines, we'll have oxygen corrosion. So in the steam lines, you should be checking your deaerator for performance of removing non-condensable gases, one of them being free oxygen from the feed water and the makeup water. The standard in the industry, or ASME standard, 7 parts per billion oxygen or lower. 7 parts per billion or lower. So just to go a little bit on the correction roadmap, the thing about it is that if you can inject amines into the steam system and then just get with the chemical supplier and see what he has available for countering CO2 corrosion. Condensate lines, I really would prefer you use stainless steel, but that's your preference. If you don't, use Schedule 80 piping. Do not use Schedule 40. Steam piping, as I was saying, the area should be tested twice a year, and that's dissolved oxygen test. And there's a standard, ASME standard for doing that task, which means remove the sulfite from the deaerator operation and do the test, and your level should be 7 parts per billion or less. Now, same thing as you should go out in your steam system and check for dissolved oxygen out in the steam system. Out in the steam system, we do not want more than 80 parts per billion out in the steam system. And people ask me, the deaerator's in operation. How do we get air into the system? Startup procedures. People do not vent air from the steam lines at startup, and then do not vent air very well from the process, and we get air entrainment. So those are some of the things that you can do for your correction roadmap. Water hammer. 4 types of water hammer: hydraulic flow, differential, thermal shock. I can talk for 3 days on water hammer. Solution: no water hammer. No steam system should have water hammer. 0. There's no reason for it. If you do have water hammer, you hear that pinging, banging, just remember one thing. It's telling you you've done something wrong. Come and fix me. Otherwise, it's going to do damage. So the thing about a water hammer, can take piping, elbows out, cracked valves. The list goes on. And then my only comment with water hammer, if you hear it, go out and make corrections. You should not have water hammer. It's a very, very safety issue. And so no water hammer. Erosion. Yeah, small leak today will be larger tomorrow. The thing is that the steam will wire draw, erode the materials causing a leak. So you get them around threaded connections, we get a leak, and just continues to grow and grow and grow. And we do have processes where we cannot shut down. I used to be in charge of a power plant, and I only had 1 shutdown per year. the thing with the shutdown, if I had steam leak, I had to wait for 300 days till my next shutdown. So it does cause issues and stuff like that. There are people in the field, in the industry, that will come in and fix steam leaks online. So if there is a steam leak and you cannot shut down, you might want to take a look at these people, and they'll come in and seal the leak. They will not fix the leak. They'll seal the leak online. So anything on steam leakage, we really want to be proactive. And the proactive is changes. What are we going to change to stop the leak from occurring again? And that's where it's proactive. So, production leaks will create system pressure losses in the system, which will basically lower pressures, lower temperatures. So on small applications, process applications, it becomes very, very problematic. Larger applications, not so much. But small applications, we get steam leaks. When you lose pressure, we lose temperature. The thing with steam, it's, if you have 100 psi, it's 330 degrees. If you don't have 100 psi, you're not going to get 330 degrees. So if you have steam leakage, you have lower pressures, you're going to get lower temperatures. And then basically that's really why you want to be proactive. Reliability. One of the things is the reliability of valve selections. And so the thing is for one thing is reliability, you got two things. You got code. So the code, either you're on ASME, the boiler code, or you're on B31.1 or B31.3, you're under some code. And the code says the valve has to be rated for the highest pressure and temperature, which is where the safety valve is set. The code doesn't tell me that the valve can be very unreliable or it can be reliable. So you have to, as a buyer of components or designer of components or operator of a system with components, you have to look at the valve and determine if it's going to be reliable or not. We do have valves that we put in the steam system, and the vendor has a lifetime warranty on the valve. Lifetime. And then we have valves that can go in the system to meet the code, and the warranty is when you take it out of the box. There is no warranty, okay? It's going to leak like a river. So the thing is that valves, we should be getting somewhere around 30 years operation out of a valve without any issues. Same thing with steam trap selections, leakage through the bonnet of the steam trap or through the side of the steam trap. Again, we have two things, code and a reliability. Steam traps, minimum 15 years operation, anything below 300 psi. Blowdown valves, same thing, material selections. My thing is material selections, the thing is that I only use cast steel and stainless steel. I'm very, very seldom ever use cast iron valves in the steam system. For one thing is code issues and things like that. So I'm always looking at cast steel or stainless steel in my valve selections to get the reliability that I want in the system. So safety. Thing is that I come into the plant and then I got safety training on Monday morning at the plant. Coming up here, and they're going to tell me if I climb a ladder, and then if I do this, I need my SL2 monitor and H2S monitor and all the things. And I really do want to be safe. I really do want to be safe. And then I go out and I have to walk through steam leaks and condensate leaks, and my safety glasses get fogged up with the steam and I can't see, and it creates a problem. And steam condenses to condensate, creates water in the air. In colder climates, believe me, it freezes and causes hazard, ice formation. I've been in plants where they can't go into one segment of the plant because of all leakages, just straight ice. So there's a multitude of reasons, to correct steam leakage, and safety is one of them. Remember, OSHA says 140 degrees. Part of your program, this is a vital point. Just don't go out and fix the leaks and then expect it not to leak again. You got to do root cause analysis, and it has to be part of the management program. It really, really does. You have to understand failure, and once you understand failure, make changes to improve the system. Change has to occur from design, installation, selection of products, vendor selection. Change has to occur. So the thing is that just don't go out and fix leaks, because the leaks will come back again. So make changes. Don't accept leakage as normal. It's abnormal. I've been in very, very large plants that have 4 steam leaks and think that is outrageous. I've been in plants that have 400 steam leaks and don't think anything about it. So make it a normal not to have steam leaks and abnormal to have it. So